Welcome back. In this video, we are going to explore mutually exclusive and independent events. Our objectives here are to define mutually exclusive events. We'll take a look at the probability of the union of two events. We'll look at the probability of mutually exclusive events. We'll define independent events, and we'll explore the probability of independent events. Objective 1, define mutually exclusive events. Well, two events, A and B, are mutually exclusive when A and B have no outcomes in common. In the terminology of sets, the intersection of A and the intersection of A and B is the empty set. Essentially, if you have A, then B is impossible to have. If you tossed two dice, the event of rolling a sum of 6 and the event of rolling a sum of 9 are mutually exclusive. This next thing I think is important. To find the probability that one or the other of two mutually exclusive events will occur, you can add their individual probabilities. That would be the probability of A plus the probability of B gives you the probability that one or the other will occur. Here's the probability of the union of two events. If A and B are events in the same sample space, then the probability of A or B occurring is given by the probability of A plus the probability of B minus the probability of the intersection of A and B. So what we're saying here is if we've got the probability of two things occurring, there could be an intersection or a possibility that both of those do occur. And we have to subtract those out. If A and B are mutually exclusive, then the probability of the intersection of those is 0. So then the union would just be the probability of A plus the probability of B. So I talk about that down here. If the probability of the intersection of those is 0, then A and B are mutually exclusive. So here's a sample. Let's take a look at this. One card is selected at random from a standard deck of 52 playing cards. What is the probability that the card is either a heart or a face card? So we've got this deck. We pick out a card. We want to know the probability that it's a heart or a face card. Some of you that play cards a lot may know right away, well, wait a minute. Some of our face cards are hearts. It could be both a heart and a face card. We've got a Venn diagram over here on the left where they list all of the cards that are hearts. And in another set, they list all of the cards that are face cards. And sure enough, we've got an overlap here. The king, queen, and jack of hearts are both hearts and face cards. They fall into both categories. So those will need to be subtracted out to find an accurate probability. To find the probability, we first will take a look at the probability of selecting a heart. Probability of A selecting a heart, since there's 13 hearts, that would be 13 over 52. We could reduce this, but we're going to leave the denominator at 52 because we're going to have a common denominator here. Similarly, we have 12 face cards, so the probability of selecting a face card is 12 out of 52. Now keep in mind, we have those 3 cards that are both face cards and hearts. Since we have those 3, we need to subtract those out. But the probability of selecting one of those 3 is just 3 out of 52. So we apply our formula. We add the probability of the first 2, then we subtract the possibility or the probability of the overlap, and we get the following. The probability of A union B is the probability of A plus the probability of B minus the overlap, those face cards that are hearts. Adding that together, we get 22 out of 52, or putting it into your calculator, 0.423. Objective 3, we're going to take a look at the probability of mutually exclusive events. The Human Resources Department of a company has compiled data on the numbers of employees who have been with the company for various periods of time. The results are shown in the table. So we've got our years of service. Nothing overlaps here in our years of service, and the number of employees for each of those sample sets of years of service. There's a good possibility we'll need the total of employees depending on the question, so that's something to keep in mind. So we're asked, an employee is chosen at random. What is the probability that the employee has 4 or fewer years of service, and B, 9 or fewer years of service? Indeed, we will need the total number of employees, so we'll have to add all those together. We'll have to add them all up and get that total, and then that's going to be our possibilities, and then our winners will be those with 4 or fewer years of service. Another set of winners will be the 9 or fewer years of service, which 9 or fewer years of service, most of you guys are going to look at that and go, well, that's all those guys, so we're going to add those two together, and indeed that is what is going to happen. So our solution, we'll add the total number of employees. There's 529 employees. The probability for A is to calculate the probability of 0 to 4 years of service. There were 157 employees, so 157 out of 529. The probability of 5 to 9 years of service was 89 out of 529. We can grab that right off our table. But question B asked for 0 to 9 years of service, so we have to add the 157 and the 89. The probability of the union of A and B is the probability of A plus the probability of B. Being 0 to 4 years of service and 5 to 9 years of service are mutually exclusive. You can't be in both of those groups. You're in one or the other. That's why we can simply add those together, and we get 246 out of 529. Intuitively, or the way the question was asked, you probably knew that you would take all those with 9 or fewer years of service right away. In Objective 4, we're going to define independent events. 2 events are independent when the occurrence of one has no effect on the occurrence of another. For instance, rolling a total of 12 with 2 6-sided dice has no effect on the outcome of future rolls of the dice. So one roll of the dice doesn't impact the next roll of the dice. It's a little bit like me wearing my lucky socks when the Packers play. I think they have an impact on whether they win or lose, but those are really independent events. To find the probability that 2 independent events will occur, multiply the probabilities of each. The probability of independent events is just the probability of A times the probability of B, and we have done this already. A sample for you: a random number generator on a computer selects 3 integers from 1 to 20. What is the probability that all 3 numbers are less than or equal to 5? The probability of selecting a number from 1 to 5 is 5 out of 20, or 1 out of 4. It's got a 1 in 4 chance of selecting 1, 2, 3, 4, or 5. So 5 out of 20, or 1 out of 4. Each selection is independent. So they select the first time, they've got a 1 in 4 chance. They go back, they select a second time, they've got a 1 in 4 chance. They go back the third time, they've got a 1 in 4 chance. Okay, we have assumed replacement here, so 1 out of 64. Another sample might look like this, given a 2-sided coin and a die. So I've got my coin around here somewhere. I think I put them away. I've got my coin. I can either flip heads or tails. And I've got my die. I can roll a 1, a 2, a 3, a 4, a 5, or 6. What is the probability of flipping a head and rolling a 2? Well, flipping a head would be 1 out of 2, because I can only get heads or tails. And rolling a 2, I get a 1 out of 6 chance. So multiplying 1 out of 2 times 1 out of 6, I get 1 out of 12. That's the probability of flipping both ahead and rolling a 2. Sample 5, a little bit longer word problem. In 2014, approximately 44% of the adult population in the United States said their cell phone would be very hard to give up. In a survey, 10 people were chosen at random from the adult population. What is the probability that all 10 say that their cell phone would be very hard to give up? 44 out of 100 said that their cell phone would be very hard to give up. Well, that means anytime you ask an adult, there's a 44% chance that they say that. Well, asking one adult is independent of asking the next adult, and that's independent of asking the next adult and the next adult. Really, if you're going to ask 10 adults, each one of those is an independent ask with a 44% chance of them saying, yes, it would be very hard to give up. Here at the bottom, you can see it's the probability of that occurring 10 times. Well, the probability is 0.44 for the first person, and then the second person, it's also 0.44, and the third person, it's also 0.4, 10 times in a row. So 0.44 raised to the 10th power is this probability. Not very many, so pretty small chances there. 0.000272 is what that comes out to. So there's a little explanation of mutually exclusive and independent events as how they relate to probability, and you'll get some more practice with this when I see you in class.